Hi, time for a quick bit. Today, I want to talk about quantum measurement statistics and eventually their role in understanding quantum contextuality and quantum non-locality. So, we want to think of quantum systems, or more generally, just physical systems, as those for which us, an experimenter, have some inputs, and then there's some process, some experiment, some set of tasks which give us outputs. And in this case, we're going to restrict ourselves to a finite dimensional setting. So there's a finite number of inputs and a finite number of outputs. Now, each time we can think of these inputs as some knob, which we can think of perhaps as measuring a physical system at a certain angle, but it could be something more abstract than that as well. We can think of picking a particular setting, call it I1, and then performing this measurement, getting one of the outcomes. And every time we randomly select one of the inputs, we get an output, and we collect those outputs and form a statistics. After many, many trials, we are able to, with some confidence, say that those collected tabulated statistics form some sort of probability distribution, one for each set of inputs. Now, we're not going to talk too much about the quantum end today. Suffice to say that there is, we can think of quantum systems in a landscape of physical systems, and quantum systems have the particular property that you obtain these probabilities that you get in this scenario using a particular set of rules with a thing called a quantum state, and then some sort of positive operator valued measure. Now, we don't need to talk about what these are, but I'm just saying that there are additional ingredients, and the probabilities that you get from quantum mechanics are kind of like a subset of what you would in principle be able to obtain. And so you get these probabilities using this Born rule. Okay, so that's all I want to talk about the quantum part for right now, and then we'll return to that a little bit later. So you can ask, okay, isn't this a sort of restricted setting? What is going on inside this black box? So what you might want to ask is like, okay, we have this sort of set of inputs, and then it reveals an output. Now, can we dig deeper in some sense? Can we sort of have some causal mechanism for what is causing these outputs? Now, trying to explain statistics in this way is an approach that goes back to Einstein, Podolsky, and Rosen. These are called now hidden variable theories. And the basic idea is that there's some ontological, or there's some physical states out there in the real world whose perhaps complicated dynamical process ends up giving you a certain set of outcomes. Now, if you had just happened to known what that underlying complicated process is, you could perhaps figure out what these outcomes were with some amount of certainty. But the uncertainty of quantum statistics comes from the fact that we don't have access to this finer level of detail. And so one of the things that Bell and others most notably have been able to do is to put this sort of idea up to a test. The notion that there are some physical states out there, and that it is due to their complicated interaction that you are able to obtain these quantum statistics. So how does that work? So we're going to look at a sort of simple version of this problem due to Clauser, Horn, Shimoni, and Holt in 1969. Suppose we have two distant parties, Alice and Bob, and they each have two possible inputs. Now, Alice could choose X0 or X1 as an input. Bob could choose Y0 or Y1. And altogether, there's four possible input settings that they jointly have: X0, Y0, X0, Y1, X1, Y0, X1, Y1. So those are pictured right here. And in each time there's a setting, we have two outputs, 0 and 1. So jointly, there's the 2 bits, there are sets of bit strings that could happen for each possible input. So 0, 0, 0, 1, 1, 0, and 1, 1. And we can collect this sort of statistics as before into a nice table. And then there's a sort of nice feature of this table, which I will discuss next. More or less, the idea is the following, that I can't just have any old numbers appearing in here. Of course, these probabilities, each of these cells is a probability distribution that sums to 1, but we have additional constraints as well. Namely, that these parties, Alice and Bob, are distant from each other. So it should be the case that Bob cannot affect the outcomes of Alice and vice versa. Should you be able to do that, then this would violate Einstein's special relativity. So we call this the non-signaling principle, which enforces this the principle of special relativity. Namely, the way that this is done is, suppose you have some setting of Alice, xi, it could be 0, x0, or x1, and there's some tabulated probabilities and statistics, but all that Alice ever sees is her particular statistics. That is, on her end, she only sees some distribution of zeros and ones. So it should be the case that when you add up, so in the top row, these include all the outcomes where Alice gets outcome 0, and outcome 0. You add those probabilities together, that is, you marginalize, and that gives you this top number. Similarly, for getting this bottom number. Now, it shouldn't matter whether Bob chose y0 or y1. So even though these numbers individually do not have to be the same, their sum should be the same. So this is the principle of special relativity. And the way that we want, and so the nice feature of this table is that we sort of have that the horizontal rows have to sum up to the same value, the same with the second row, like this, and these as well, so on and so forth, as well as the vertical columns. So we do not just allow any table of probabilities, 16 probabilities in this case. We only allow those that are normalized and those that satisfy this set of equations written more explicitly here. And just, you don't have to understand the details too much. Just know that this is going to ensure at a minimum that you do not have this superliminal communication going on. Now, how can we sort of feed hidden variable models into here? How do we know whether a set of probabilities like this can be understood as coming from some sort of like basic set of physical states, which may be undergoing some complicated process? So there's one way to understand this in this case. We can think of each input as representing us measuring a particular element of reality. So we can think of, so for each x0, we get an outcome that's 0, 1. So we can think of x0, when we press x0, we're measuring a particular coin, which could be heads or tails, 0 or 1. x1, the same thing. It could be a different coin. And that's also 0 or 1. So we have here a hidden variable model where we can take this experimental apparatus described above and give it some concrete states. More or less, there are 4 possible coins. When Alice measures x0, she's able to obtain the values of the brown coin, say, and when she measures x1, she's able to obtain the values or heads or tails. She's able to unveil the underlying value of a particular coin. Same thing with Bob. So we say that we're making a couple of assumptions here, namely that when we press an input, we're measuring something. We're measuring something out there. So in some hand-wavy sense, these inputs correspond to some physical variables, some elements of reality. And we're also assuming locality, that these physical variables are spatially localized. That is that we do not allow, we want to think of these coins in some sense as not affecting. So the value, the fact that this is heads or tails does not affect anything, or rather, maybe the better way to put it is that unveiling the value of this is not going to change the value of something over here. Those are the two assumptions that we want to make. And so how many possible ways are there to arrange these four coins, which could all be heads or tails? Well, because we know, due to this assumption of realism, of course, real coins out in the real world always have some value. They're always heads or tails. And so no matter what the situation is, there's always going to be some set of values for each of these coins. They could be all heads, or they could be heads, tails, and altogether there's 2 to the 4th equals 16, all the way to tails, 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 tails. And we call these deterministic distributions. These are just the sort of like states that are possible within this hidden variable model. I mean, there's no other options. You could either have that these variables they're either heads or tails, and there's 4 of them, so there's 16 possible states. Now, of course, we're not restricting ourselves to only these 16 possible states. In the real world, you can imagine situations in which, just like a real coin is not either heads or tails, it's some probabilistic mixture. We can also think of these probability tables as being composed of probabilistic mixtures of these deterministic sort of extreme cases. And if that is the case, then we call them classical distributions. That is, they're classical because it's a probabilistic mixture of situations in which you have something that's real and local. Heads, 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 tails, so on and so forth. Now, turns out to be the case, and this is actually realized in quantum theory, that you can have non-classical distributions. Now, I'm not going to give you an example from quantum theory, but instead a sort of post-quantum set of distributions, PR boxes due to Popescu and Rohrle. And this is not realizable in quantum theory, but it's an example of a very simple example of a non-classical distribution. What does that mean? It means that you can't possibly write it as a probabilistic mixture of those 16 states that I wrote before. It's something else. It's something outside of that set. Not only is it outside of that set, it's also outside of probabilistic mixtures of those vertices. So this brings us to, so now that we're talking about something being classical or non-classical, we can talk about Bell inequalities. Well, what are Bell inequalities in a sense? Bell inequalities, if you are in a sense just a certificate of classicality, if you satisfy all the Bell inequalities, it means that you can write that. So if you have a table of probabilities and they satisfy, so a Bell inequality is just a linear expression that has to be less than or equal to some constant. It could have some coefficients. We think of each of these 16 probabilities in this table as a variable, and it could have some weighting on it. That's all that I'm doing. You don't need to dig too deep into the details, and it should be less than or equal to some constant. Now, how you determine these coefficients and constants relies on some more advanced mathematics we're not going to get into, but the basic idea is that there will be some set of inequalities like this, and if you satisfy all of them, that is, the value that you get for this table is less than or equal to that constant, then it guarantees that you can write this table here in terms of probabilistic mixtures of these classical pieces. And so more geometrically, we can think of each of the deterministic distributions as being sort of like a vertex in some space. And then we can think of sort of convex hull. What does that more or less mean? It means that we're allowing all probabilistic mixtures of those points. And so if you satisfy the Bell inequalities, you are inside of this set, inside of the so-called convex hull, which we call the Bell polytope. And if you don't satisfy, and so the inequalities will be something like these faces, they determine the outside most part of this set of possible classical distributions. And if you do not satisfy any one of these, then you're outside, and we call it non-classical. This is the crux of the Bell inequalities. These are where things like CHSH inequalities come from. They come from being able to determine whether a distribution can be written in this possible way. So I hope that this was sort of a nice introduction to quantum measurement statistics and how these end up relating to notions of non-classicality, Bell inequalities that you've probably heard about, but maybe didn't know too much more, didn't sort of know in any more detail. So hopefully this is an intermediate sort of level of sophistication between pop science and something where you have to read a textbook or a research article. Okay, thank you. Hope this was useful.